Okay, thanks, Serena, for the introduction. Before starting to talk about math, let me say that it's an honor and a great pleasure to be here. So thanks to Serena, Christian, and Robert for organizing, and it's an honor to contribute to celebrate Jacob. So today I'm going to talk about Huang-Yang-conjecture for the low-density Fermi gas. I'm afraid, or I'm sorry, if many of you maybe already attended some talks regarding this topic here. Hopefully today I will manage in 40 minutes to give you an overview of what we finally understood last May. So my talk is going to be based on a series of works which I mentioned here. So let me start with an introduction. I think here I can go very fast because it's exactly the same setting introduced by Jan Philipp for bosonic system, but in this case for spin 1/2 fermions. So we have n spin 1/2 fermions in a box in R3 with periodic boundary conditions, and this is the Hamiltonian describing the energy of the system. Of course, now we work with fermions, so we work on the antisymmetric Hilbert space. And interaction is spin independent, so we can fix exactly number of particles with a given spin. This is the notation I'm going to use. And as often is, or so far often is the case, the interaction is going to be positive, radial, compactly supported, and in L2. I think we can ask a bit less than L2, but this is what we wrote in our paper, so this is what I'm going to report in the slides. The object we would like to study is the energy density, which is exactly the object Jan Philipp already introduced. So, and of course, this depends on the density of spin-up and spin-down particles. So we would like just to understand how this quantity behaves in the dilute regime, which means, as Jan Philipp said, and as in many other talks appeared already, that rho A cube goes to 0, where A cube is the scattering length of the interaction potential. So regarding this object, there was an old conjecture which goes back to 1957 by Huang and Yang. They conjecture the expansion of the energy density at in the first 3 orders. So let me comment a bit on the meaning of those terms. So, and before doing that, I put these slides because I always forget to say the following. So here I wrote that we suppose, or that in the conjecture, maybe it's supposed that that you have same numbers of particles spin up and spin down. So rho up is equal to rho down equal to rho half. And then if you look to this term, this is 2 pi a rho square. But if you want, the right way to think about this is to look at it as 8 by a rho half times rho half, where one rho half is density rho up, and the other one is density rho down, meaning that these contributions are there only because there are correlations between different species of fermions. Otherwise, if you have only one species, you will not see the rho square and also the 7/3 contribution. So with respect to fermions, there is a difference. The first order correction is indeed of kinetic type. And you are all experts, so I go very fast here. You know that if you want to minimize kinetic energy, you just have to, you can consider just uncorrelated states. For fermionic systems, uncorrelated states are Z determinants. And since we want to minimize kinetic energy, a good reference state is the free Fermi gas, where you take Z determinants of plane waves, which are normalized in the box, so that you minimize the kinetic energy, meaning that all the plane waves have momenta inside the Fermi ball, which we suppose to be field. This is not a loss of generality. And then if you consider this state here and you compute the energy per unit volume, you recover exactly the kinetic contribution, which is the one appearing here. Here I wrote in the general setting when rho up is in principle different than rho down. And then you get a contribution over the rho square, where you see that there is a V hat 0 and not the scattering length. Yes, this A is exactly the scattering length, which is there also in the bosonic expansion for the energy density. And then at second and third order, you see other constants in which indeed also a parameter is appearing, A or A square. This is the scattering length, which means that beyond the kinetic type error, there are other terms which are there because of correlations between particles. And understanding those two terms is exactly the goal of this talk today. So regarding rigorous results, I already said, this is nothing else than the proof of the Huang-Yang-conjecture under those assumptions on the interaction potential. And this is, so this result is proved in two different preprints. One is an upper bound and the other is a lower bound for the energy density. And as I said maybe already, this theorem, I wrote it again under the assumption that we have equal number of spin-up and spin-down fermions, but in our paper, we wrote that this holds in for any type of combination of the two species. It's just, you just have a different constant here, and this is a typo. This should be, if I write that this is true, this should be as before 2 pi a rho square. Okay, so I have quite some time. So the first thing I would like to do is to compare with the literature. So in the last years, many contributions appeared, but let me say that the first order corrections were understood already in 2005 by Lieb, Seiringer, and Solovey. And then later in 2021, together with Marco Falconi, Christian Hainzl, and Marcello Porta, we published a paper in which we recover exactly the first two contributions, but with different techniques, which is indeed the basis of what I'm going to tell you today. And then I improved a bit this result, at least for an upper bound in 2023. There are also some related results, which are about studying fermions. This system here at positive temperature. This was done by Robert in 2006. He understood the behavior of thermodynamic pressure in the first two order corrections, which you could, if you want, compare to those two. Then recently, Chen, Wu, and Zhang produced two preprints in which they study ground state energy in the Gross-Pitagevsky regime of the same setting, and in which they study also dilute Fermi gas at very low temperature, so so temperature which are a bit far from the Fermi temperature, rho to the 2/3, which was instead included by Seiringer in 2006. And then I said that those two terms are there because of correlations between different species of fermions. You can ask yourself what happens if you have only one species of fermion. And then this was studied by Lauritsen and Seiringer from 2023 to now. They investigated both the zero temperature case and the positive temperature case. And a few weeks ago, it appeared also a preprint by Gamet, in which he studies the dilute Fermi gas spin 1 alpha in the inhomogeneous setting. So I think in the last years, many interesting papers appear regarding this problem. Okay, so since we are here to celebrate Jacob, I wanted to put these slides on the bosonic picture. So this asymptotic appeared already many times yesterday, and this is the Huang-Yang formula for the analogous setting you could consider with bosonic particles. And here I try to mention the contributions starting from leading order, in particular lower bound, where we already heard that Lieb and Ingvason gave the first proof. And then there are many people who worked on the Huang-Yang conjecture. And then, as we heard in Benjamin talks yesterday, now we are also able to go beyond the Huang-Yang in the thermodynamic limit, at least as an upper bound. So thanks, Jacob. I also enjoyed a lot reading your paper. Okay, after that, the plan is to slowly go with you to the main ideas of the proof of the Huang-Yang conjecture. So we start moving to second quantization, meaning that we rewrite the Hamiltonian using fermionic creation and annihilation operators. And what we understood so far is that in the Huang-Yang conjecture, the first order is of kinetic type, and this is the energy of the free Fermi gas. So if you want to start to understand correlations, the first thing you have to do is to remove the energy of the free Fermi gas from your system and to really isolate what is the energy, the correlation energy. So to do that, you can think about taking your Hamiltonian and conjugating it with a unitary transformation, R, over the Fock space, which you can call particle-Hall transformation. The main job that the conjugation does is the following. If you have a fermionic creation operator with momentum k outside the Fermi ball, you just don't change anything in your picture. But if K is inside the Fermi ball, then what you're doing is to switch the creation into an annihilation and the annihilation into a creation operator. So you are creating holes inside the Fermi ball and particles outside. Yes, sorry, indeed. I didn't want to mention, but you forced me to mention. This is a minus K. So sorry, this is another typo. And then, so if you consider this transformation and you take a state in your Fock space, which has exactly the right number of particles you would like to work with, and you compute now the new energy after the conjugation, then what turns out is that you recover the free Fermi gas energy plus the correlation energy. So then from now on, I will refer to this object here as E free Fermi gas. And all the point is to understand how to deal with this correlation energy and, of course, what is relevant and what is subleading with respect to the order you would like to reach in the energy density expansion. So then I'm not going to talk about the full correlation energy, but about the effective correlation energy, which means the part of the correlation energy which is important to recover the rho 7/3 contribution. If this is your goal, then you can think about the correlation energy as a sum of three operators. The first one is again of kinetic, a single particle operator. This is of the form A star A. And this is indeed the kinetic energy with a new dispersion relations. Kf is the radius of the Fermi ball. And the new dispersion relation is there because the energy of the free Fermi gas is already included here. So this is just the new kinetic energy. And then you have two other type of interactions, which we call Q2 and Q4. So numbers here refers to the number of particles outside the Fermi ball. So let me focus first on this. This is the main object you have to understand in order to prove the conjecture. So this is about interaction of two particles with momenta p prime and p inside the Fermi ball, which are those. And then they interact through a potential V at k, and they jump outside the Fermi ball with two new momenta, p plus k and p prime minus k. So the reason why those are 4 A stars is because we are conjugating our Hamiltonian here with respect to R. So then, in principle, you could think about A star p prime like DAs. And Q4 is also relevant, is instead the same type of interactions, but between two particles which are outside the Fermi ball, which interact and they remain outside. So those are the two main operators which are going to play a role. And here in gray, I wrote also another part of the correlation energy, which for me is not in the definition of the effective correlation energy, because this operator is not giving any contribution up to the 7/3 term. But the problem is that if you consider your ground state or any approximate ground state, then it's not easy to see immediately that the Q3 defined here is subleading with respect to 7/3. So in particular, at the level of a lower bound, we had to work a bit also with this term here in order to prove our theorem. I will go back to this later, but just for a generic picture, the sum of those three is the right effective correlation energy. And once we arrive here, of course, there are already some estimates to do. You have to discard over approximate ground state expectation of the rest of the correlation energy. Then you should understand how to deal with this. And there are two main things I think are important to discuss together. The first one is the following, that one of the main ideas is to understand how to describe what we want to describe. So we want to describe low energy excitations around the Fermi ball. And it turns out that those kind of excitations can be described in an efficient way by new creation annihilation operators, which are called B or B stars in our papers. So those operators are given by pairs of fermionic operators. One fermionic operator has momentum inside the Fermi ball and the other outside. And if you remember the definition of the operator Q2 I gave before, you can understand that this is indeed the right operators to work with in order to understand this kind of excitations. And let me say that those operators were used also in other settings, in particular in high density Fermi gases in fixed boxes by many, I think, all people present here. I don't want to mention because otherwise I would forget some of them. And then those operators, it turns out that they are quasi-bosonic, meaning that they almost satisfied, up to some errors, canonical commutation relations. And this is what I already said, that the operator which I call Q2 is the relevant one to understand to work with to prove our conjecture. And if you remember the definition of Q2, this was the definition. And if you use now the new creation annihilation operator, you notice that this quantity can be exactly rewritten using the quasi-bosonic creation annihilation operators. And I forgot to say in the previous slides that all of those approximations here stays there because effectively, again, only interaction between different species of fermions here and there are important, but in principle, you have to discard all the rest. But for a picture, this is only the type of, only those interactions are the relevant ones. Okay, this is one idea or one tool that you have to do, use those new quasi-bosonic creation annihilation operators. And the other thing that you would like to do is to understand which is the right scattering equation or the right or how to think about the scattering process you would like to describe. And in our setting, the right scattering equation, which effectively describes correlations up to the order we want, is this one. So just notice that if you would not have this term here, this is the usual zero energy scattering equation. And what it turns out to be true is that this is the right scattering equation to be used under the assumptions, under the following assumptions on the momenta. So now again, you can think about R and R prime as the momenta of the two particles inside the Fermi ball interacting and jumping outside after the interaction. So we are describing exactly this scattering process, the one included in Q2. And I think this is a way to write these objects here, but I think it's better to look at it written in the following way, like differences of momenta. Indeed, if you think about what we are doing, again, we are considering interactions between particles inside the Fermi ball, jumping outside with new momenta under these constraints. And so then if you look to this difference here, this is just the difference of the square of the momenta before and after the interaction, and also this thing here. And now, if you think about bosons, when you study bosons, what you want to do, at least at the beginning, is to study fluctuations with respect to the condensate, which is at p equal to 0. What we want to do is to study fluctuations or excitations with respect to the Fermi ball. And because of that, if you want to compare this to the bosonic picture, you should put R and R prime equal to 0, and then you see that here, R plus P and R prime minus P give you exactly the 2P square, which is appearing in the zero energy scattering equation in the bosonic picture. So somehow this is one way to think about why, or to understand why this is exactly the same scattering process, but describing fluctuation around the ball and not around a condensate at P equal to 0. And this is going to be a remark which is going to be useful later. So if you look to this equation here, then you see that if the momenta P if the momentum P is very large, in particular is much larger than the radius of the free Fermi ball, then you can think about the solution of this scattering equation, which can be written like that, almost like this quantity here, where you replace this object by the p square, just because r plus p, and this is another type, r prime minus p, is dominant with respect to those two other objects. So this means one way you can think about this is that if you look to the Fermi ball from very far away, of course, the Fermi ball looks like almost the condensate at p equal to 0. So for high momenta, studying excitations with respect to the Fermi ball is not so different than the bosonic picture. But as soon as you go closer to the Fermi ball, then you have to care about the presence of the Fermi surface. And this is what you do if you include the full scattering equation in your analysis. And indeed, now I would like slowly to go with you to all the orders. Meaning, first I would like to understand the rho square and then the rho 7/3. So to understand the rho square, you can really compare the picture, at least to the bosonic one. In the rho square, you can think that only high momenta are contributing, and then you are looking to the Fermi ball from far, and this looks like a point somehow. And this is why, in order to recover the rho square contribution, what you can do is the following. You take your effective correlation energy, which is again H0 plus Q2 plus Q4, and you try to do what was done for the bosonic setting. Meaning now we understood that Q2 can be written exactly with respect to those new creation, annihilation, BB star operators. And then what you can do is to try to do a Bogoliubov transformation like the bosonic one. So if those B's were the bosonic creation annihilation operators, this is exactly what you do to recover the first order correction in the energy of a bosonic picture. So take this, the same Bogoliubov transformation, which is only quasi-bosonic because B are quasi-bosonic, and put here as a phi the solution of the zero energy scattering equation. Then if you conjugate the effective correlation energy with respect to this unitary operator, what you get up to many errors is again the sum of those two operators plus a constant. And the constant looks like this one. It's rho up, rho down times integral of V phi times the volume. And then this gives you intuition of what could be a good triassate. So far I'm only talking about upper bound, and then when we go to 7/3, I give you an overview of upper and lower bound. So as an upper bound, this thing here tells you that as a good triassate, you can take the vacuum, and then you apply several unitaries. The role of R we already discussed, and then now what you want to do is to investigate a bit better correlations between particles, which we are not doing through the R, using Bogoliubov transformation. And notice that this state here is a good triassate because it has exactly the right number of particles. So if you compute the energy over this triasstate, first thing that you do is to basically consider the action of R over H, and this we already did. You end up with this quantity here. You have energy free Fermi gas plus the correlation energy up to having now these new unitaries because you are putting it there in the definition of the triasstate. R is the particle Hall transformation, the one that allows you to do this splitting. And then if you insert this thing here inside there, then of course those two disappears because you have the vacuum, and it remains up to many errors, just the right constant you like to extract. So now why this is the right constant? Because if you again remember the expression of the free Fermi gas, this was the right kinetic contribution plus rho up, rho down, V at 0, that you can rewrite as integral in the x of Vx. If you adjust this contribution with the new constant coming from Bogoliubov, then here you recover this number, which is exactly the 8 pi a if you choose phi as a solution of the zero energy scattering equation. And also, a remark is that I told you that at some point, in particular in the lower bound, the operator Q3 is going to be a problem for us. But according to our definition of triasstate, because of some orthogonality between spin components, you can prove that expectation of Q3 over your triasstate is equal to 0. So for an upper bound, the Q3 is not important at all and actually doesn't give contributions. So far, I'm going to try to do to give you an overview, and of course I'm skipping many technical details. All of this is only philosophical picture. You cannot really do that in thermodynamic limit, so this is already abuse of notation. This is a solution in R3. We are working on a box. You have to do some localization to make all of those approximations rigorous and so on. But those details I skip because I just want to give you the big picture. Okay, so now I hope that you agree that we understood how to compute the rho square. So this is trial state. If you want to do lower bound, you just use your ground state here, and almost the same analysis also, meaning you can use conjugation by unitaries to prove also a lower bound up to the rho square precisions. And this is what we did in the first paper I mentioned, together with Marco Falconi, Christian Hainzl, and Marcello Porta. And then in my second paper, I just understood a bit better how to define this Bogoliubov transformation in order to get, in all of those approximations, an optimal error, which is of the order rho square. Okay. And now we go to understanding the rho 7/3 contribution. So I just did 2 slides with the key ideas or with the key tools. One is using quasi-bosonic creation annihilation operators, and this somehow we already did here in the definition of Bogoliubov transformation, and the other is to use the right scattering equation, which is describing the right excitations around the Fermi ball. And so far, we didn't do that at all. We put just zero energy scattering equation. And if you remember my comment from the previous slides, it means somehow that we only consider contribution coming from very large P, because so far we just consider this kind of solution of the scattering equation up to some approximation. So now then we agree that to understand rho 7/3, the somehow only thing that we have to do is to replace the scattering process with respect to the true one, the full scattering equation, under the constraints I mentioned already before. But if you were with me so far, so this is then in one line, this is the idea, replace in the definition of Bogoliubov transformation the simple or the zero energy scattering phi with the solution of the full scattering equation. And if you are with me so far, what I try to underline is that you can think about phi RR prime like phi for large momenta. And then it turns out that instead of replacing the phi in the unitary for all momenta by the phi RR prime, it's much more convenient to think about the Bogoliubov transformation as a product of 2 other Bogoliubov transformations of the same type, because both of them are quadratic in the B operators. But in such a way that we are effectively implementing the behavior of phi in your unitaries, meaning that if your momentum P is large enough, in particular far from the Fermi ball, recall that the Fermi ball has a radius rho to the minus 1/3, and for me this gamma is positive. Then you can think about this phi as the simple phi, and then this is the transformation you can perform for I momenta. And as soon as you want to work closer to the Fermi ball, then instead you have to consider the full solution, the solution of the full scattering equation, which is this one. So at the level of the upper bound, this is the main idea. And in the next slide, what I would like to highlight with you is which is the role of B1, which partially we discussed already before, and which is the role of B2 in the computation of the energy. So first, now we update our definition of trial state. Before we had R e to the B omega, and now I try to convince you that it's convenient to think about R e to the B1 e to the B2 omega, where B1 is high momenta and B2 is low momenta. Not really, thanks. So according to what I wrote here, yes, because you in principle, you can think about P being either above this or below, but then since we work in thermodynamic limit, we want to have a smooth conditions with respect to being high or low. So there are some errors which are not contributing at all, but that you have to deal with. Thanks. I forgot this remark. Okay, so now again, we start from the same point we started before. So what we do is to start to conjugate H with respect to R. And then, as we learned, conjugation by particle all, isolate free energy Fermi gas up to the correlation energy over the right trial state. Now, which is the role of B1, is similar to the one of before. But now I'm really using the fact that I look only to high momenta. So if you compute this quantity here using the rule I gave you before, what you find is that this gives you H naught plus Q4 plus a constant. And the constant now, it's 8 pi a rho square up to an error, another constant, which is there because now in B1 you only consider contribution coming from high momenta. So if in principle what you get is the right somehow 8 pi a rho square for only P large. So if you want to recover the right 8 pi a rho square, you have to adjust that by what you are missing from low momenta. And notice that here I didn't write, so in principle, if I consider this, I should write H naught plus Q4 plus a constant, plus what remains from the conjugation of Q2, again leaving at small momenta, because low momenta you are not basically considering in the first unitary. I didn't write the Q4 because this operator here is an error. So all of those inequalities are true up to errors, meaning that this operator is important only for high momenta. As soon as you compute contribution coming from high momenta, then you can think about the new thing the new object to understand like the sum of those two, which is kinetic energy plus an operator which is of the same type as Q2. But if you remember, in Q2 there was a V hat K. Now in place of V hat K, you have 8 pi A, which is just the new renormalized interaction that you can renormalize exactly because you are conjugating with respect to B1. So high momenta gives you this. This is the new now effective correlations energy you would like to understand. And to deal with this, you consider the action of this B2 transformation. So now if you compute the conjugation of this new effective correlation energy with respect to B2, what you get is that something is disappearing because now you test over the vacuum, and then you have the right constants from before, those two, and then what you do is to adjust or to recover the right rho to the 7/3 correction, which is here. I hope that, yeah. Yeah. This. Yeah. Yeah, exactly. This is why I wrote it here. So this is exactly there because of this thing here that, as I said already before, in principle you recover only this contribution for a momenta, then you adjust for low momenta, you miss something, and what you miss is indeed important to recover the right 7/3 correction. And if you now put everything together, what we proved is an upper bound over the energy density with the right behavior up to the 7/3 correction, up to some errors. Maybe this is a good slide to make a comment. So also here I'm ignoring many technical things that we had to solve. One is the following, since this is written. So maybe it's better to go to the definition of B2, no, it was better to go here. So remember, in the definition of B2, there is this kind of denominator appearing because you want to deal with the full scattering process. But if you look to that, you see that for us, R and R prime are inside the Fermi ball, and R plus P, R prime minus P are outside. So of course, you have a singularity in all the Fermi ball surface. And then in order to deal with this, what we had to do indeed was not to consider the B2 I wrote before, but the B2 in which the denominator is this one plus an epsilon of the right order in rho, which allows you to do not have any singularity. But of course, then if you want to recover the right constant, you have to remove this regularization. So this is one thing that we did to avoid singularities around the Fermi ball. And also I'm writing all of those things in momentum space because I think this gives you a good understanding, but since we work in thermodynamic limit, all the errors I'm not mentioning at all have to be estimated in configuration space. So you have to change picture from momentum to configuration and try to estimate all the things. And as you can imagine, dealing with B2 in configuration space requires a bit of work because this is really something which is explicitly written in momentum space. Okay, and the remark again is the same. In B1, B2, we are not changing the distribution of B's in the definition of the unitaries. Is always quadratic in the B, like B up, B down, minus B star down, B star up. So because of this spin dependence, also for this updated trial state, the contribution of Q3 is 0. So for an upper bound, you don't have to care at all about the cubic term. Now, in the last slides, we move to the main ideas for the lower bound. In the lower bound, we didn't use, I have 10 minutes, right? 5. Sorry, I thought 10. Okay, in the lower bound, what we did was to not perform unitary transformation, but to do completion of the square, meaning you want to rewrite your energy like something which looks like A star A plus a constant plus error terms. And then what we do is to look to those positive operators, kinetic energy and Q4. Now I change picture. I wrote Q4 in configuration, meaning that so now if you look to the U, if you see the U means projection outside the Fermi ball. So this is exactly A star AA with all momenta outside the Fermi ball. And the idea is that we want to rewrite the correlation energy in this way here, so that the constant is indeed the right one, and the A star A you can ignore because this is positive at the level of a lower bound. Okay, now I go, so I was planning everything. I was going quite slow because I thought I had 10 minutes, but now I have 5, so I discussed only completion of the square for Q4. So now I would like just to let you understand how we do the completion of the square, or how we guess which is the right completion of the square for Q4. For an upper bound, what we did was to think about, to consider the product of those two Bogoliubov transformations. Now, if you remember, I mentioned that Q4 is important only for I momenta, so meaning only in B1, where the scattering process was the zero energy scattering one, so was what I denoted by phi. So you can think, for effectively for Q4, you can think about this product as the transformation we had before, now written in configuration, where you have zero energy scattering solution, and then you have B up, B down. So now this V is projection inside the Fermi ball. So this pair is the B up of before, and this pair is the B down of before. If you want to understand the action of this over Q4, then it's enough to understand the action of this unitary over the pair AU-Y, AU-X. And if you compute this object, then what you get is AA to leading order, and then you get plus phi AV, AV. So this gives you the intuition of which is the object you should use to complete the square of Q4, meaning that you can think about Q4, which in principle is A star AA with all U's, like adding this extra contribution and then subtracting some things exactly because you want to recover the identity. And then I would like just to tell to you that if you do that, basically you are implementing conjugation by the unitary to leading order. Indeed, if you look to the object you are subtracting, so the first one is V phi, and then you have we said that this is a B sigma, and this is the big sigma prime. So this is exactly the form of Q2 in which you do not have interaction V, but you have interaction V phi. So the orange terms gives you minus Q2 V phi, and the green term gives you AA star with all V's, meaning all momenta inside the Fermi ball. And if you put this in normal order, of course, you recover a constant, which is what we were recovering with our high momenta Bogoliubov transformation. So now I go to the end because I'm done. You can do the same with H naught. In H naught, of course, the full phi should be included, so the completion of the square is a bit more complicated. But again, it's the same story. You complete the square. then you have something positive that you can ignore, and then the two terms that you are subtracting up to many errors are giving to you the Q2 and the constant you would like to extract. Now, again, you are considering the full scattering process, so you recover both the rho square part of the rho square contribution and the Huang-Yang constant. So this is the conclusion. This is what we get from the two completion of the square. Then if you put on the other side the Q2, this is exactly the effective correlation energy we wanted to understand at the beginning. And then what we realize is that the sum of the green terms gives you exactly the rho square contribution plus the Huang-Yang constant up to many errors. And this is, okay, I had a comment which I skipped. This was about the role, how we deal with Q3. Basically, with Q3, you need to refine your completion of the square in order to ignore its contribution, which is not possible at the beginning. And if you do that, then you are done with the proof of the lower bound. Before saying thanks to all of you, I also have a picture. So this is a bit more recent than the one Jan-Philipp showed yesterday. But according to my memories, this is the first, maybe it's not the first conference where I met Jacob, but for sure it's the first one where I had the occasion to talk with him. So first he was the chair of my contributed talk. And there I was talking about Ginsburg-Landau theory, where I used tools which are very close to the theory about rotating condensates. And I remember that after my talk, it was very nice to talk about those topics with Jacob. Also, the same day, we were sitting at the same table for dinner, and I enjoy a lot to talk about with him, and he reported many stories of his life that I still remember. So it was a great pleasure. Happy birthday, Jacob, and thanks to you for the attention.